Hello, hello, hello. Yes, I guess I'm clearly audible. Yeah. Good evening. Good evening, audience. Very good evening. Yes, because today is the sound chapter. There is a sound from my voice. Yes, it is effective a sound. Of course, different kinds of parameters in the sound. Welcome to Physics Cartoon Camera. Welcome to Physics Cartoon Camera. Welcome to Physics Cartoon Camera. Yeah. Oh, some companies also are reaching to me. Unknown companies, yes. Some of the institutions. Most welcome to all the audience and very grateful to all of you. Physics is one of a subject. Yes, children will get little attention on that, and they're feeling very difficulty. As I'm the physics teacher in my country, so my it's my grateful to reach to the rural India students where they can able to learn the physics chapters, and I'm sure I'll give complete value to on my chapters. I'm confident about my physics chapters. Hope it will clear all your doubts, and I'm expecting there is a good result in your academics. Yes, welcome to all again. Physics cartoon camera, the main introduction over here. I would like to say that yes, we are offering the invited talks and science facts, recording classes. Many are there, you can see in the description. Each and every division will be scheduled properly. Yes, I am trying to reach to all the country students, especially rural India. Now today, the concept of class 9 standard. Up to yesterday, we have studied about motion, force and loss of motion, gravitation, work and energy, and some of the question and answers you might be observed. Yes, who are all missing the live stream classes, you can able to see the recording classes over here. And if any doubts are there, you can able to email me. Till now, who not subscribed, subscribe the channel and promote to village students especially. Shall I start my class? Yes. Now today, sound chapter of class 9th standard CBSE. In this sound chapter, we are learning about what is sound, production of sound, propagation of sound, reflection of sound, range of hearing, applications of ultrasound, and structure of human ear. We will see step by step now. So, what is sound? Sound is a formation of energy. Can you produce sound without utilizing your energy? Which form of energy did you use to produce sound? Yeah, sound. I'm listening. I'm listening from the audience. Yes, there is a sound. I'm listening outside the vehicles. And many parameters what we are listening. Sound is a form of energy which can produces a sensation of hearing in our ears. So, production of sound. Production of sound. How sound will be produced? Take a tuning fork and set it vibrating by striking its prong on a rubber pad. Bring it near to your ear. Did you hear any sound? Touch one of the prongs of the vibrating tuning fork with your finger and share your experience with your friends. Now, suspend a table tennis ball or a small plastic ball by a thread from a support. Okay? Touch the ball gently with the prong of vibrating tuning fork. Observe what happens and discuss with your friends. Yes, sound is heard. On touching the prongs, vibration is felt. Ball gets displaced from its mean position and starts moving on being touched by the fork. From this, we can conclude that the vibrating tuning fork strikes the ball and produces motion. A similar thing might be happening in the production of sound. We will see. Now fill water in a beaker of glass up to the brim. Gently touch the water surface with one of the prongs of vibrating tuning fork. Next, dip the prongs of vibrating tuning fork in water, which is shown in the figure 2. Observe what happens in both the cases. Discuss with your friends why it's happening. You can observe there are the two glasses with full of water and hit the tuning fork and put it like horizontally. Other one is vertically like this. So what we are observing? Both the cases, sound will be produced from the vibrating fork which produces a ripple in the water. Ripples are produced which moves up and down. Ripples produced moves sideways. Is this because of direction in which sound travels? So above activity, we have produced sound by striking the tuning fork. We can also produce sound by plucking, scratching, rubbing, blowing or shaking different objects. In last two activities, we set object vibrating and produced sound. Vibration means a kind of rapid to and fro motion of an object, what we can call it as a sound. The sound of human voice is produced due to vibration in the vocal cords. When a bird flaps its wings, do you hear any sound? Yeah, we are hearing the sound. So propagation of sound. How sound will be propagated? Take a different musical instruments. So which part of the instrument is giving sound is matters. Sound is produced when a skin or a membrane of a drum vibrates, which is in a drum. In a guitar, sound is produced by vibrating the stretched strings. While plucking that, we can get the sound. So how does sound travels from one place to another place? So what is the medium over here? Let's check. One student, let him put on the ear on the table. Another student, he is knocking gently. So the student can able to listen the sound. So here the bench, which is a solid, through the solids, yes, waves can be transmitted. Now in this second experiment, the boy put the ear on the surface of the water. From the down, he rang the bells. Automatically sound is produced. Why is the sound called as a wave? Because sound travels exactly the way wave travels in a medium. Sound waves are characterized by the motion of particles in the medium and are called mechanical waves. Okay. When an object vibrates, it sets a particle of the motion, the medium around it vibrating. The particles do not travel all the way from the vibrating object to the ear. A particle of the medium in contact with the vibrating object is first displaced from its equilibrium position. Then it exerts a force of adjacent particles, as a result of which the adjacent particle gets displaced from its position of rest. After displacing the adjacent particle, the first particle comes back to its original position. This process continues in the medium till the sound reaches your ear. So this I'll explain in a very simplest way. I'm speaking, you are listening. While I'm speaking, yes, through my vocal cord, there is a vibrating object which vibrates and given the voice. While giving the voice, what's happening? Each and every air molecules which is giving vibration. Even keep on the vibrations, what's happening? It is giving next molecules energy. Each and every molecule is giving energy to the next molecules. If this process continues, yes, sound will reach to the destination. Next. Now, while the sound propagating, there are the two different types over here, compressions and rarefactions. What is compression and what is rarefaction? All the molecules which is high denser over here, that is compression. And the molecules are separated, that is rarefaction. Okay. Air is the most common medium. Air is the most common medium through which sound travels. When a vibrating object moves forward, it pushes and compresses the air in front of it, creates a region of high pressure. This region is called compression. Okay, wherever the high pressure is there, wherever the density of the molecules are more, that is called as a compression. So when the vibrating object moves backwards, then what happens? It creates the low pressure region, that is rarefaction. So you are observing the dotted lines are very more, which means density of the air molecules are very more over here. Then this is compression. If all the air molecules are separated, okay, that is rarefaction. As the object moves back and forth rapidly, the series of compressions and rarefactions is created in the air. This makes a sound wave that propagates through the medium. Compression is the region of high pressure and rarefaction is the region of low pressure. Pressure is related to the number of particles of the medium, which is given volume. More density of the particles in the medium gives more pressure and vice versa. So how does sound produced by an object reaches to our ear? Sound is a mechanical wave and it needs a material medium like air, water, steel, etc. for its propagation. It cannot travel through vacuum. Let's check. Hope you know bell jar experiment. In bell jar experiment, take a glass jar and cut the top and put a rubber cork over there. Put a hole to the rubber cork, put a rod over there and connect it to electrical bell. Then electrical bell connected to switch. From the down surface connected to vacuum pump. Here what's happened? Switch on it. Now bell ringings we are listening. Switch off. Again collect entire the air which is inside of the bell jar, collect it out. So there is a vacuum is created. While vacuum creation, again switch on the bell. The bell ringings we unable to listen. The bell ringings we unable to listen, which means sound needs medium to travel. So we made it as a vacuum. That's the reason we unable to listen it. Now explain how sound is produced by your school bell. When the bell vibrates, it pushes adjacent particles to vibrate. This creates a series of compressions and rarefaction. This makes sound to propagate through air. Why are sound waves called mechanical waves? Sound waves forces medium particles to vibrate. Some mechanical work is done in this process. So, sound waves are called mechanical waves. Suppose you and your friend are on the moon. Will you able to hear any sound produced by your friend? Sound needs medium to propagate. Since moon has no atmosphere, propagation of sound is not possible. Now, sound waves are longitudinal waves. Longitudinal waves contains compressions and rarefactions. So where that density is very more by the air molecule, that is compression. Where the density of air molecules are less, that is rarefaction. We will study further. Take a slinky. Slinky, you can extend it. Slinky in the sense of you can able to purchase like a circular coil kind of thing. Children can play it. Once you can freely suspend it, you just give a jerk. What happens? We are getting something compressions and rarefactions. Compressions and rarefactions. Clear? So these compressions and rarefactions we can able to compare with our like sound propagation. Okay. So there is the dot marked always moves backwards and forwards for its position. You can put a small points over there. You can see small up and downs over there. Now this implies that medium of the particles are not travel. Only energy is transmitting, not the particles. Okay. Now types of waves. Types of waves are two types. One is longitudinal wave, other one is transverse wave. What is longitudinal wave? Medium particles oscillate in a direction or parallel to the direction of propagation wave, that is longitudinal wave. Transverse wave, medium of particles oscillate in the perpendicular direction to the motion of a wave. Sound waves produced by earthquake, vibrations in string, ripples in water. Alright. Just compression and rarefaction. Compression having high density, rarefaction having low density. Compression high pressure, rarefaction low pressure. Compression represented by crest and trough, and rarefaction trough or valley. Rarefaction will be trough and valley. Now characteristics of a sound wave. Wavelength. What is wavelength? The distance between two conjugative. Here in the transverse wave, what happened? The transverse waves will oscillate from a mean position. In this mean position, you can see that there at the top end, that is called as a crest. The down end, we can call it as trough. Crest and troughs will be there over here. In longitudinal wave, compressions and rarefactions. In transverse waves, crest and trough. The distance between two crest or the distance between two trough is called as wavelength. The wavelength is usually represented by lambda. SI units meters. So it tells us how frequently an event occurs. Suppose you are beating a drum. How many times you are beating the drum per unit time is called frequency of your beating the drum. We know that when sound is propagated through a medium, the density of a medium oscillates between maximum value and minimum value. The change in density from the maximum value to the minimum value, again the maximum value, makes one complete oscillation. The number of such oscillations per unit time is frequency of the sound wave. If we cannot count the number of compressions or rarefactions that crosses per unit time, we get the frequency. Frequency in the sense of the number of oscillations in a unit time, as simple as such. Okay. Now time period. As simple, time taken for one oscillation, we can call it as time period. Fine. The frequency and the time period, frequency nu is equal to 1 by t. Next one is pitch. A violin and flute may both be played at the same time in an orchestra. Both sounds travel through the same medium, that is air, and arrives at our ear at the same time. Both sounds travel at the same speed irrespective of sound. but the sounds we receive are different. Why it's happening? In an orchestra, we are observing that all musical instruments at a time we are listening, but we can able to differentiate what is the instrument. Why it's happening? Due to pitch. How the brain interprets the frequency of an emitted sound is called as a pitch. The faster the vibration of a sound source, the higher is the frequency and higher is the pitch. Fine. Thus, high pitch sound corresponds to more number of compressions and refractions passing through a fixed point per unit time. Next, amplitude. What is amplitude? The magnitude of maximum disturbance in the medium on either side of the mean value is called amplitude of the wave. It is usually represented by the letter A. For sound, its units will be that of density or pressure. Clear? What is amplitude? Very simple, well explained. The deviation of a wave from a mean position. The deviation of a wave from a mean position we can call it as amplitude. Now, which wave property determines loudness, pitch? Guess. Which sound has a higher pitch? Guitar or car horn? You can see that amplitude of a sound wave determines loudness. Louder the sound has the greater amplitude and vice versa. Frequency of the sound wave determines the pitch of the sound. Okay. Sound of a car horn has a higher pitch. The speed of a sound is defined as the distance between a point and a wave, such as compression or rarefaction. We know that speed is equal to distance by time, which is lambda by t. Here lambda is a wavelength of the sound wave. It is the distance traveled by the sound wave in one period of time. Thus, speed is equal to wavelength into frequency. The speed of a sound remains almost the same for all the frequencies in a given medium. Now, sound wave has the frequency of 2 kHz and the wavelength of 35 centimeters. How long will it take to travel 1.5 kilometer? You can see that the given data, the frequency they have given 2 kHz, which means 2000 Hz. Wavelength 35 centimeters, which is 0.35 meters. We know that the wave, like the speed is equal to lambda into f. So once we can derive over here, v is equal to f into lambda. How to derive it? Very simple way. For example, the wavelength. What is wavelength? The distance between two crest and trough. Two consecutive crest or two consecutive trough is called as a wavelength. Or the distance between two compressions or rarefactions, we can call it as wavelength. Now velocity is equal to distance by time. We know that. So the distance in the sense of here, wavelength lambda by t. We can write 1 by t into lambda. So 1 by t nothing but frequency. Frequency into lambda, that is velocity. So based on that, frequency they have given 2 kHz, that is 2000 Hz. Lambda will be 35 centimeters. We have to convert into meters. Now they're asking velocity is equal to wavelength into frequency. Wavelength is 0.35 meters and frequency will be 2000 Hz. So 700 meters per second. Fine. Characteristics of a sound wave are frequency, amplitude and speed. So what are the wavelength, frequency, time period and amplitude of the sound wave? Wavelength. Wavelength is the distance between two consecutive compressions or rarefactions. Frequency. The number of sound waves produced in 1 second is called frequency. Time period. Time period is time taken to produce one wave of sound. Amplitude. Amplitude is the maximum displacement along the mean position of the particles of the medium. Fine. Now, how are the wavelength and the frequency of a sound wave related to its speed? You can see that the relation between frequency and wavelength of a sound, velocity is equal to wavelength into frequency. This means that the speed is equal to the product of wavelength and the frequency of a sound wave. This equation is also called wave equation and applicable to all types of waves. Now there is a question. Calculate the wavelength of a sound wave whose frequency is 220 Hz and speed is 440 meters per second. So as you know the formula, V is equal to F into lambda, lambda is equal to V by F. So just substitute 440 by 220, which is 2 meters, is the wavelength. Hope it's clear, all the audience. If any doubt is there, yes, you can chat. If any doubt in the sound chapter, the audience can able to chat with me, or in the description, my email ID, you can write any question related to sound. I'll answer for that. Next, a person is listening to a tone of 500 Hz sitting at a distance of 450 meters from the source of the sound. What is the time interval between successive compressions from the source? Now frequency is equal to 1 by t, t is equal to 1 by frequency, which is 1 by 500 Hz, 0.02 seconds. Clear? Next one is intensity. What is intensity? The amount of a sound energy passed each second through unit area is called as intensity of a sound. We sometimes use the terms loudness and intensity interchangeably, but they are not the same. Distinguish between loudness and intensity of sound. Loudness of a sound is determined of amplitude and intensity of a sound wave is determined by the frequency of sound wave. Loudness is a measure of the response of the ear to the sound. Even when two sounds are equal intensity, we may hear one as louder than the other simply because our ear detects it better. So speed of a sound in different media. Okay. In which of the three media, air, water or iron, does the sound travels the fast at the particular temperature? At particular temperature, sound fast in iron because it's a solid. Speed is maximum in solids. Yes, sonic boom. When the speed of any object exceeds the speed of a sound, it is said to be traveling as a supersonic speed. When a sound producing sound moves with the speed of higher than that of a sound, it produces shock waves in air. These shock waves carry a large amount of energy. The air pressure variation associated with the type of shock waves produced a very sharp and loud sound can be called sonic boom. The sonic waves produced by supersonic aircraft have enough energy to shatter glass and even damage buildings. Now, reflection of sound. Like light, sound gets reflected at the surface of a solid or liquid and follows the same laws of reflection. The direction in which the sound is incident and is reflected make equal angles with the normal to the reflecting surface, and the three are in the same plane. Okay. Now, take two identical pipes. You can make the pipes using chart paper. The length of the pipes should be sufficiently long as shown. Arrange them on a table near a wall. Keep a clock near the open end of one of the pipes and try to hear the sound of the clock through other pipe. Adjust the portions of the pipes so that you can best hear the sound of the clock. Now measure the angles of incident and reflections and see the relationship between the angles. Lift the pipe up the right vertically to a small height and observe what happens. Angle of incidence is equal to angle of reflection. When pipe is lifted, we are unable to hear the sound anymore because angle of incidence is not equal to angle of reflection. Both these points confirm that sound follows the laws of reflection. Echo. Whenever you are going to empty room, yes, we are observing echo. If we shout or clap near a shootable reflecting object such as tall building or a mountain, we hear the same sound again little later. The sound which we hear is called an echo. So what is the minimum distance required to echo? The sensation of a sound passes our brain for about 0.1 second. To hear the distinct echo, the time interval between the original sound and the reflected one must be bare at 0.1 second. If we take the speed of a sound 344 meters per second at a given temperature, say 22 degrees centigrade in air, the sound must go the obstacle and reach back the ear at the listener on the reflection after 0.1 second. Hence, the total distance covered by the sound distance is equal to speed by time. So 344 by 0.1 approximately 34.4 meters. We are hearing the distinct echoes. The minimum distance of the obstacle of the sound must be half of the distance, which is 17.2 meters. So reverberation. What is reverberation? Sound propagates through a medium at a finite speed. The sound of a thunder is heard a little later than the flash of a light is seen. So we can make out that sound travels with a speed which is much less than the speed of light. The speed of a sound depends on the properties of medium through which it travels. The speed of a sound in a medium depends also on temperature and pressure on the medium. The speed of a sound decreases when we go from solid to gaseous state. In any medium, as we increase the temperature, the speed of a sound increases. For example, the speed of a sound in air 331 meters per second at 0 degrees centigrade and 344 meters per second at 22 degrees centigrade. A person clapped his hands near a cliff and heard the echo after 5 seconds. What is the distance of the cliff from the person if the speed of a sound? Speed of a sound will take 346 meters per second. Now you can see speed of a sound 346 meters per second, hearing the echo of t is equal to 5 seconds. So the distance is equal to v into t, which is 346 into 5, 1730. By half of the distance, 865 meters. Clear? An echo returned in 3 seconds. What is the distance of the reflecting surface from the source? Given that the speed of a sound is 342 meters per second. You can see here the speed of a sound is 342. Time will be 3 seconds. Distance is equal to speed into time. So 342 into 3, which is 1026 meters. Exactly by 2, that is 513 meters. So uses of multiple reflections of sound. Why are the ceilings of concert hall curved? Since concert hall is big, so audience at the back rows, the hall may not hear clear sound of speaker. To overcome this problem, the ceiling of the concert hall is made concave. Concave ceiling helps the sound waves to reflect and send to farther distance, which makes the concert hall unable to sense the clear sound and the audience even still in back rows of hall. So range of hearing. You can see that human auditory field 20 hertz to 20,000 hertz. Above the 20,000 hertz, we can call it as ultrasounds. 20 less than infrasonic sound. A reverberation. The repeated reflections that sound in the persist of sound is called reverberation. A sound created in a big hall will persist by repeated reflections from the wall until it is reduced to value where it is no longer audible. To reduce reverberation, the roof and the walls of the auditorium are generally covered with sound abundant materials like compressed fibers, rough plasters or draperies. So what is the audible range of average human ear? That is 20 hertz to 20,000 hertz. What is the range of frequencies associated with infrasound and ultrasound? Infrasound will be less than 20 Hz. Ultrasound will be more than 20,000 Hz. which is 20 kHz. Applications of ultrasound, which is the most common question. Yeah. Ultrasound is generally used in clean parts located in hard to reach places. For example, spiral tubes, odd shaped parts, electronic components, etc. Detect cracks and flaws in the metal block. If there is even a small defect, the ultrasound gets reflected back, indicating the presence of the flaw or defect. Now, applications of ultrasound. Heart treatment we are using, and ultrasonic waves travel through tissue of the body and gets reflected from a region where there is a change of tissue density. These waves are converted into electrical signals that are used to generate image of the organ. Next one is sonar. What is sonar? Sonar is a device that uses ultrasonic waves to measure the distance, direction, and speed of underwater object. And how it is? The transmitter produces and transmits ultrasonic waves. These waves travels through water and after striking the object on the seabed gets reflected back and are sensed by the detector. The detector converts the ultrasonic waves into electrical signal, which are appropriately interpreted. Let the time interval between transmission and reception of the ultrasound signal will be t, and the speed of a sound will be v. The total distance will be 2d because up and down. So 2d is equal to v into t. The above method is called echo ranging. The sonar technique is used to determine the depth of the sea and locate underwater hill, valley, submarine, icebergs, and sunken ships. Now there is a question. A ship sends out ultrasound that returns from a seabed and it is detected after 3.45 seconds. If the speed of ultrasound through the seawater is 1531 meters per second, what is the distance of the seabed from the ship? So how to answer this question? The same formula, 2d is equal to v into t. So the time transmission is 3.42 seconds they have given, and the speed of ultrasound in a seawater is 1531 meters per second. Distance traveled by the ultrasound is equal to 2 times of the depth of the sea, which is 2d. 2d is equal to 1531 into 3.42, which comes as a 5236 meters. By 2 if you do, 2618 meters, approximately 2.6 kilometers. Okay. Next question. A submarine emits a sonar pulse which returns from the underwater cliff in 1.02 seconds. If the speed of a sound in salt water is 1531 meters per second, how far away is the cliff? So this kind of questions is the same. Now the sound wave 1531 meters per second, time t is equal to 1.02 seconds, distance is equal to speed into time, 1531 into 1.02, which is 1561.62. Again by 2 you can do that, 780.81 meters. Now the structure of ear. Without ear, we can't hear. Yes, here is a mandatory organ. Ear allows us to convert pressure variation in air with audible frequencies into electrical signals that travels to the brain via auditory nerve. You can see here there is a pinna, eardrum, middle ear, Ascending tube, inner ear, and ear canal. So here sound collected by pinna and passes through the auditory canal to eardrum. Next, compressions and rarefactions causes eardrum to move in and out, creating vibrations. Vibrations are amplified by ear bones. Middle ear transmits these vibrations to the inner ear, where these are converted to electrical signals by cochlea. Next, any queries, you can able to send an email to me. And from next 2 days, we are starting with class 10th standard CBSE. And all over the country the students you can able to join every day 10 to 11 p.m. So daily Monday to Saturday I'm spending 1 hour time to the students of rural India especially. So I'm expecting CBSE model papers and CBSE concepts, a session and reasoning questions, case study based questions. So maximum gathering, and I'll explain. You can utilize this. If any questions are there, yes, are there in the description my email ID. You can ask the question. So who are all not subscribed, subscribe and you will get the notifications. And every Sunday there is a science fact will be released. What we are observing. You can see the description what physics cartoon camera is providing you. Thank you so much. Have a great day. Good night. Jai Hind.